So joining me here now is Baihan Lin, who's representing work on unified models of human behavioral agents in bandits, contextual bandits, and reinforcement learning. Welcome, Baihan. It's great to see you. And let me ask you the same question I'd like to ask our speakers in the very beginning. Please tell us a little bit about yourself and what brought you to the intersection of good mental health and AI.
Well, hi everyone. I'm Baihan from Columbia University. Thanks for RJ for introducing me, and it's nice to join the discussion with you all. And the first question is how did I actually get into the field? So I remember when I was in middle school, actually one of my close friends actually committed suicide due to major depression, and we know that the education back in China can be quite stressful, but his unfortunate choice was beyond my comprehension at that time. It was also the first time that I started to realize how vulnerable human minds can be. So since then, I become interested in the field of psychology and actually gradually learned that the mental health is a more and more prevalent problem in our society in general. And I started to organize this kind of mental health support services and groups back in high school and also later in my college. And I hope that at least I can make some sort of differences to people around me in any way that I can think of. However, deep inside my heart, I also wish to probe and solve this problem from a more internal aspect. So actually during the college, I chose to double major in psychology along with my other major in applied and computational mathematics. I have always hoped to actually combine my engineering skills to impact the society in the field of the mental health. So currently, I'm actually pursuing a PhD in Columbia University on computational neuroscience, and my research is mainly to develop new computational models and machine learning algorithms to facilitate our understanding of the neural mechanism of human decision-making and also complicated perceptions, either in their healthy states or in their clinical variants. So although I'm not really a clinical medical student per se, but my ultimate goal is to pursue translational research that can actually provide scalable and interactive tools to assist like clinicians or physicians for critical medical decision. So in my doctoral study, I'm also part of the computational psychiatry team at the IBM T.J. Watson Research Center, where we actually have a lot of active and exciting projects that involved, say, multiple psychiatric conditions in different data formats and different stages of medical intervention. And I think that it is actually currently, it's a fantastic time to work on all those topics because it's really a digital era where tons of data can potentially provide critical support for case-based reasoning in clinical practice. And I'm very looking forward to the discussion and potential collaborations in these projects. And I would love to have more conversation with you guys either here or offline. So that's how I get here.
Excellent, Baihan. Thank you for that rich description. So let me ask you about the problem that you are addressing in this paper. How did you come to that problem? Why do you consider it to be an important problem?
Yeah, so for this problem, when I was a medical intern in the psychiatry specialty back in Nanjing Brain Hospital during my sophomore year, the DSM-5, where every psychiatry knows, just came out. So we were asked to actually familiarize with all the long list of updated definition of many mental disorders. And I have to say those psychometrics and also clinical descriptor for each of the disorders took me quite some effort to memorize. And they are quite heterogeneous in so many ways. So in many cases, my supervisor, colleagues, and I have to go through a bunch of different measurement forms and transcript to make even simple diagnosis, which is kind of similar to a computational phenotyping algorithm or flowchart would do. However, I also witnessed that in many scenarios, there's actually an additional barriers that creates a huge gap between the mental health care and also the mental health problems. At least back in China, unlike in many Western countries, actually seeking this type of mental health therapy is not a common thing. And especially in those suburban cities, and can be actually viewed as being weak or dramatic instead of having a real problem. So this factor actually greatly reduced the actual number of people actually physically visit a doctor from the actual huge population of people that actually needs this type of mental health attention. So one recent development that I found quite powerful is actually this digital health, and also the ubiquitous computing, where people can just easily use their cell phone, smartphone, or other device to record their health-related data. And behavioral data like that has also enabled the research field in psychology to investigate many clinical conditions with like simple cognitive tasks like gambling or something like that. So the question that I'm interested in is that can we actually perform computational phenotyping on this kind of behavioral data? In another word, can we enable the users to simply perform like simple cognitive tasks and receive medical advice or other support just given those interaction history? For instance, can we develop like an app where the patient can just play a game and we can tell them what conditions you might have and offer some cogent medical advice accordingly? So to accomplish that, one major obstacle is actually a lack of universal model across different mental disorders. So like my example in the DSM-5. So given our past experience in various topics like on attention and also reinforcement learning of the brain, we finally decided to focusing on the reward processing system as the core neural processing mechanisms, which is supposed to be distinctive among a wide variety of clinical conditions. So eventually we build upon the traditional reinforcement learning model and incorporate like 4 expressive reward processing parameters. And so that's how we arrived at our current project.
Excellent. So this really speaks to the power of digital health. The statistics are that more than half the people who need mental health care do not seek out classic care environments because of just being discovered in the act of seeking out care. And so there is a lot of promise in building these systems, both for assessment, as you're suggesting, but then also for boosting capacity and helping them navigate the next steps. So Baihan, let me ask you to share some of your slides that describe your results. I will go off screen and please share those with the audience.
Can everybody see my screen, or is it sharing the right
good.
screen?
We're not in slideshow mode yet. There we are, all good.
Okay, so are we in the slideshow where we only see the
Yes.
slides, right? Okay, cool. Yeah, so basically the motivation, like I mentioned, is that from the evolutionary psychiatry point of view, all these type of mental disorder, they actually lies on a manifold or a continuous spectrum where all those disorders are actually extreme points that actually arises during evolution for multiple purposes. So ideally, if we can model the entire manifold properly, we can actually do this type of behavioral mapping and for downstream predictive modeling and stuff like that. So on the other hand, from the AI perspective, those extreme versions can also be beneficial in specific environments. So we can build better algorithm based on that. We pay attention to 3 levels of reinforcement learning problem. The first level is the multi-arm bandit, where each action actually corresponds to the reward function of certain options. So for instance, if you have 3 options, which one you want to, which action you want to take. And the contextual bandit is more complicated, where you are also given a context or the current state that you can take as a prior information to make your current decision. So you are trying to learn, you are trying to make an action based on the current information that you accumulated and try to make the optimal action that maximize your reward. And the full reinforcement learning problem actually involves paying attention to multiple contexts across multiple states, because your current action can change your current state that can yield a different story where you need to pay attention to the previous history or the future outcome as well. So to deal with that, we propose this 2-stream framework where everything that was processed would be separated into the positive domain and the negative domain, where this we draw from inspiration from the neurobiological research, where how the brain actually perform the neural circuits dealing with the positive reward and negative reward tends to be different, and they follow different rules. So that's why we have this clean cut of model, and more specifically, during an action selection process, your agent or your human subjects that we want to model would be taking account into the representation from both domain, and you would also be revealed with the reward feedback from the positive and negative domain as well. So given that setup, we have the flexibility to model a wide range of clinical conditions. Shown here is a subset where we draw from a literature review, a thorough literature review of those clinical conditions. And based on their understanding, we set our parameters, 4 parameters, accordingly. So the red parameters are for reward history, how well you would remember the reward history from the past, and also the blue parameters are the reward perception, how you would perceive the current reward feedback that you have. So we tested on multiple cases. Shown here is an example where we're showing on IO gambling task, which is a popular task in psychology and also clinical study. And we also have a lot of human data, around 600 human data here. And we also simulated our mental variance based on the parameters that we set earlier. As shown here, the reward mapping, the reward function for the four possible action is quite non-Gaussian. So it looks quite weird. So basically, you're asked to select from one of the 4 decks, and those decks has their underlying reward function, which is quite weird, as shown here. And here, shown here, is the short-term dynamic versus the long-term dynamic of all those all those agents perform over time. So shown here is the percentage of choosing the better DAX or the correct option. So you can see that they can match many clinical discovery. For instance, the black curve shown here is the addiction. And we see that addiction actually learns to choose the better DAX or the better action very fast early in the time periods. However, it was caught up by the other agents. So this was reasonable because the addiction patients tends to forget about the negative signals far more than other agents. So in the future, when you actually faces some infrequent feedbacks of punishment or negative reward, you might forget about it, and you are only learning to do myopic prediction for the reward. And some Disney plots, you can also see that they cluster based on this behavior trajectory that we accumulated. We also applied all those different mental variants as well as standard reinforcement learning algorithms on the games. So shown here is the Pac-Man game, where we let the agent to play for 1,000 rounds, and also not only in the classical way, but also in 3 type of non-stationary scenarios. And we see that in most scenarios, our algorithm, given a 2-stream feedbacks and 2-stream framework, are much more flexible than the traditional reinforcement learning. And also in certain cases, like here, the ADHD and also dementia, due to their fast switching idiosyncrasy, they actually adapt to the non-stationarity quite well and perform much better than everyone else. So here we can also see it in action, where if you pay attention to the chronic pain patient, it's quite funny because it barely pursues any positive reward, like the pack dot. However, when a ghost comes, it will try to avoid. So it only pays attention to the negative domain. So basically, that actually summarized the result where we want to connect AI with the neuropsychiatry, both in a functional way and also dysfunctional way. We want to do this clinical discovery where we can test theoretical constructs and offer insights about what's going on in those clinical conditions, and also build like humanoid AI systems. And potentially later on, we can even monitor mental health with this type of interactive system where you can simply play simple games or other type of cognitive tasks. So I will leave it to here. Feel free to contact us if you have any questions. We also open source our code and everything. Yes.
Excellent, Baihan. Thank you for that. And it's nice to hear that the source is available openly. And so this is an invitation to anybody who's listening to further experiment along the lines that Baihan mentioned. Baihan, let me ask you something that I remember thinking about while reading your paper is um, it's great to see using some of the behavioral descriptions of some of the conditions to be inspired to make richer reward functions and use that to make more performant AI methods, especially in the RL settings. I think one of your goals is to go the other way around as well, to learn from what these policies eventually learn as an effective response, given that the reward function is that, and see what that response in the AI space means for the human beings
Mm.
as what they should do to manage their condition, or perhaps manage the condition is not the right way to say it, but to perhaps come up with a better treatment or a more personalized treatment. So I'd like to hear your thoughts about, and perhaps you have some work planned in this area too on that topic.
Yeah, so I think indeed it's a two-way conversation, and our goal was not to merely build like humanoid AI agents, but also how to model the human behaviors. So actually, some of the data shown here already maps some of the human data that we collected with those behavior trajectory that was actually created from artificial agents. And we also have an ongoing project where we were directly fitting our model or framework towards clinical data. So for instance, we want to fit an agent for the Parkinson's versus Alzheimer's or specific ways like that. And we propose this in multiple methods. For instance, we attempted to use inverse reinforcement learning method to actually try to learn the underlying reward function of a certain like human expert, right? And also we also attempted to use deep network to actually match the behavior trajectory so that you can actually make great prediction. So actually we also have some development in the multi-agent application as well. Because we don't want to, we are always interacting with other people or other minds in the society. So it will be good to see how different mental variants interact with each other. So we have a paper on preprint, also under review in the NeuroIPS conference, where we let those mental variants and also different class of reinforcement learning agents play with each other on social dilemma game, like iterative prisoner's dilemma. And we also find out that our model can predict the real human data collected across different sources very well. And we also have another project ongoing in that action as well. Yeah.
Great. So I'm reminded of Chris's comments about marketing, or let's put it in other words, persuading people. And you are well aware that explainability has been an active topic of research for at least 5 years in the community. And there have been now new models of explaining RLs in particular, reinforcement learning models in particular. So when we think about that pathway back to maybe discovering what is the right reward function for somebody who exhibits a certain cognitive behavior, no matter what reward function they are living with, what is the reward function figured out through AI simulations that is then communicated back to them? What are your thoughts on communicating to them that this is actually an effective reward function outside of the graph, right?
Yeah.
Or beyond the graph, let's say. What are your thoughts on explaining that to humans in the loop, or perhaps your experience doing that?
Yeah. So let me rephrase the problem. So are you saying that because now we are both doing the prediction of how a human would be performing, but we are also having interaction backwards or feedback loop back to the human user, right? So
Yes.
how do you accommodate for the both stream and since now we are mapping like a huge graph of different users, either the artificial agent space or the human space, how do we combine these two together to make a reasonable a predictive modeling or something like that, right? So
Yeah, right. Go ahead. Yeah.
yeah, so I feel like it is indeed an innate challenge, and we are also considering those critical problems. And we also welcome all kind of collaborations on this topic. So far, my take would be, uh, so because in the AI, people tend to use, say, the Turing test, trying to fool a kind of classifier or something like that to actually create like AI that can be treated as a real human or something like that. Perhaps we can also build this type of adversarial systems or interactive system where basically the human and the computer, they are interacting continuously and they are adapting to each other. And it doesn't have to be that way because we are actually creating a new interaction. So we're not actually, and this interaction can open up an entire new space that we haven't covered yet. So regarding the marketing aspect, I also feel like we need to pay more attention on what type of interaction we want to create instead of like just going from one perspective where we want to build better AI or we want to model better the human data, but instead what kind of interaction is good interaction that can facilitate the digital health, right? So so that's
Absolutely. I think it's time for a new kind of test where we will define AIs and whether they're successful at moving our behaviors or moving our health conditions in meaningful ways in the way that other compelling human beings are. So having crossed one level of intelligence capacity, perhaps that's another metric for us to get to. So given our time, Baihan, let me thank you again for your work and let me ask you a closing question, most of which you've covered before on what would you like to see solved in this area and what kind of collaborations might you be looking for?
Yeah, so I think it's a very good question. As it's actually a growing field, there are actually many interesting things that I would like to pursue. So let me just talk about one thing, which is more recent. So we know that the big data analysis in the healthcare actually usually involves the predictive modeling, computational phenotyping, and also patient similarity. As in my slide, I also introduced about the evolutionary psychiatry perspective. Well, so basically the main idea is that all the mental disorders is in this continuous manifold. I believe this is a good viewing point to take when pursuing all three topics that I mentioned above. So the idea is that suppose we can have a continuous spectrum, we can map our behavioral data onto that and conduct downstream prediction and also medical decision. So in the current project, you see that we handcrafted this type of reward processing parameters to describe this manifold. While it offers useful mechanistic insight, we are also imposing our inductive bias somehow. So however, ideally, I would like to see that those spectrum descriptor or universal biomarkers to be not handcrafted, instead maybe unsupervisedly learned across mining across different data formats in different tasks. So I would like to welcome all kind of collaborations, both in the clinical aspect on say, valuable clinical data or psychiatric discovery, and also in computational aspect where we investigate the right way to actually interpret different data modality, like neural image, transcript, or other type of like measurement forms or all different kind of forms. So that's what I think it would be a worthwhile challenge. That's I'm proposing to the conversation, and I will be looking forward to any collaborations and discussion. Yeah.
Excellent, excellent. There is definitely a view of behavior as a computational substrate, inspired perhaps by models of physics that we can even use to predict a path to a behavior that we want to ascribe to, or behaviors that have not yet emerged in our species, but will as we add digital intelligences to a computational substrate. So thank you, Baihan, for sharing your work and your perspectives. And let me say to all attendees that please feel free to use the 5 minutes of break that we have now to connect to the authors through chat and even otherwise. Their papers and videos are on the website with their contact information. And Baihan, thanks again for your presentation, and we will talk to you again. Yeah. We will take a 5-minute break now, and we will be back at 2:45 Pacific time.